Yes, thank you, and welcome here to a panel. It's a little bit different. We've been talking a lot about the world of the large. Let's move into the world of the small. I want to set the stage here for what we're going to talk about here today with the advancements in quantum satellites by kind of taking a look back on how we got here. So imagine we're at APSCC in 1925. You know, ignore the fact that there are no satellites. You know, 100 years ago, there wasn't even this idea of quantum mechanics, at least not the way we know it and understand it today. You know, at the time, the foundation was already laid for this idea that things were different in the world of small particles. Einstein had coined the term licht quanta, this idea that light, which was already very well defined as electromagnetic waves, defined by Maxwell's equations, actually are have a particle, what we know as a photon, what he called a licht quanta, you know, the smallest element of light. And there was an understanding even today then that at the small particle quantum level, things act differently. So, for example, you know, we're all in the world of satellites. We know if you have a satellite in orbit, you know where its position and velocity now. You know where it's going to be in an hour or a day. But you translate that into kind of the small level, say an electron orbiting a proton in a hydrogen atom. The math didn't quite work out. And it got the scientists at the time to kind of think and realize that actually this is the revolutionary idea that maybe that electron isn't in one location. Maybe it's kind of spread across the orbit, defined by a probability function called a wave function, and that when you observe it, you measure it, it collapses. It collapses into a kind of a non-deterministic position. That's what we call superposition. And that non-deterministic aspect of it, again, this is revolutionary ideas, and scientists argued and debated about this, and even Einstein didn't like this idea of like a wave function collapse that was non-deterministic. And he wrote up a thought experiment that said, well, this is why I think that's problematic, and maybe you have two photons that are connected, they share a wave function, they share quantum information, they're entangled, and you separate these two entangled particles, and maybe they're millions of miles apart, and if you measured one, then the other one can't possibly collapse at the same time. But he was wrong. That is the crazy nature of entanglement. Experiment after experiment have proven that quantum superposition, the fact that the quantum states of these small particles are behind the scenes. You can only really measure it once. It kind of leads into this idea of a no cloning theorem. Hint, hint, that is actually a foundation for the security and inherent in quantum systems and quantum communications. And entanglement are all these kind of revolutionary ideas that, now over the intervening, 100 years, we've demonstrated this in the lab. We built the equipment to create quantum states and measure it. And now, here at APSCC 2025, we're putting this on satellites for very amazing and incredible applications. So I'm very fortunate here to be share a stage with two brilliant individuals and brilliant companies that are leveraging this. I'm going to start with you, Hiro-san. So Hirokazu Mori is the CSO of Warpspace and CEO of Warpspace US. So tell us a little bit about you and what you're doing at Warpspace and a little bit about your quantum ambitions.
Sure. Yeah. Thank you for the introduction. I love your passion about about quantum physics. And by the way, like I actually studied theoretical astrophysics in Cambridge, so I really love physics. my theory was also my study was about general relativity, so it's a bit different. But I really love about quantum physics as well. So I'm sorry about my voice. I spoke too much last night. I'm Chief Strategy Officer of Warpspace, and Warpspace is a Japanese startup. Our main business is traditional optical communication relay satellites and also some relevant technologies, including hardware and software. And the point here is, like, in order to utilize quantum communication for satellite communication, we need optical communication for physical layer. And we are actually developing a hardware device funded by Japanese government. And one of the applications is actually quantum communication, and I'm going to talk about it later in detail. And we have been actually developing MEO satellite relay utilizing optical communication between satellites and space to ground. And mainly, as I said, it's a traditional, like, high data rate optical communication. But in order to quantize the data, obviously, like, infrared or visible frequency is more useful than radio frequency. That's where I think a lot of discussion about quantum communication comes with optical communication. Those applications, our examples, actually you can probably find it out in US, China, Europe. Each nation in Europe are doing this. And Japan is obviously doing it, funded by Japanese government. And not just us, other companies also doing some quantum communication, like demonstration, including entanglement. Yeah, I'm happy to discuss more about it.
Very impressive. So, all right, next gentleman over is Chune Loom. He's the CEO of SpeQtral, also doing some brilliant things. So yeah, please give an introduction to what you're doing.
Well, thank you, Professor Mitlyng. Excellent introduction to quantum physics. So my name is Chune, co-founder and CEO at SpeQtral. So us as a team, we are about 7 years old now, spun off from the Center for Quantum Technologies in 2018. But our history goes way back to around 2010. And as a team, the core team from the Center for Quantum Technologies became SpeQtral essentially. And amongst us, we've launched 3 quantum payloads in space, space qualified. And we now have 2 satellites scheduled to be launched. One is for next week on Tuesday on Transporter 15, and a second one in about 18 months' time. So as a company, we provide hardware and the software to do quantum key distribution from space. The hardware is space qualified, the software is ready. We'll test out these 2 technologies in the next couple of satellites. We also have ambitions or plans to operate QKD satellite space-based QKD as a service for customers all over the world. But in a nutshell, we provide hardware. We sell the devices, custom-made for customers. And in the midterm, we're building potentially a constellation to provide QKD as a service from space. There is a second part of the business, which is on terrestrial. So terrestrial fiber-based quantum key distribution. We are building Singapore's national quantum network right now. We deployed already. We've signed on the central bank and some of the major banks in Singapore. We're working with government defense and critical infrastructures entities in Singapore and in other parts of the world. So in a nutshell, that's us. Really the global vision is that, the long-term vision is that we can build a global quantum secure communication network that will be able to provide solutions and services all over the world, and generally very open for partnerships to scale up this business.
Well, and you both mentioned, for Professor Hiro-san and Professor Chune, describe at a high level how this technology works. And I guess I would start too by, how is this, quantum communications fundamentally different than quantum computing? Because when people hear quantum, they just naturally think you're a quantum computing company. So, yeah, please.
Broadly, quantum, if you read the news, generally quantum technologies, there's 3 different pillars. So quantum computing, quantum communication, and quantum sensing. Right, we'll focus on the first 2. Now, quantum computing is easy to understand, right? You read IBM, Google, Continuum, all the big names, and they're valued at like tens of billions of dollars by now. Some of the startups that is only 5 years old. That quantum computing division has grown like crazy over the last 5-7 years. So quantum computing does compute in a fundamental way that Dave described that is different from classical computing, and it has a lot of promise to do many different, many wonderful things, right? Chemistry, financial transactions, portfolio optimization, and so on. So that's all compute, finding efficient and novel ways to do compute. But one of the things the quantum computer can do is essentially to break most of our encryption today. Think about RSA or ECC, that will be broken within X number of years. The X could be anywhere between 3 and 15 years, is anybody's guess. So come the quantum communication side of things, where as a broad concept, we are distributing entanglement throughout the different quantum computers or quantum network. That's a fundamental kind of unit of quantum communication. But one of the first applications you can do is to protect against this quantum computing Q-day, we call it, right? Quantum computing attack, using this technique called quantum key distribution, which is essentially to use quantum physics using single photons to distribute encryption keys that will not be broken by a quantum computer. So broadly, there is a very urgent need to migrate all of our encryption to something that is safe against a quantum computing attack. We call it a quantum safe transition. There's a number of solutions to address this, and QKD, we believe, will be a fundamental pillar for backbone networks, definitely, right? For backbone networks where data is very, very sensitive and where you have large volumes of data flowing amongst your data center or your customer locations.
Yeah, and maybe Hiro-san, expand on that a little bit. How you can integrate a quantum communication system with an optical communication system.
Sure, yes. So yeah, he explained everything comprehensively, but if I focus on the quantum communication and the QKD, quantum key distributions, it's easiness of actually integrating into satellite system really depends on the physical layer. So this time, compared to RF, optical communication, optical frequency has a higher data rate. So in terms of quantum physics, if you know some of the quantum physics, if it's a high frequency is higher, it's easier to basically separate into small bit in order to get some of the byte. So that's one theory. And if I may add something on top of his explanation on QKD, there are mainly two types of QKD, I would say. So it's CB QKD, DB QKD. So CB stands for like a continuous variable QKD and discrete variable QKD. And terrestrially, people are developing like continuous variable QKD, and there are lots of hotspots existing on this based on this. And we actually developing some of the like modems, hardwares, in order to utilize QKD for this kind of terrestrial grade. But currently, I think, including SpeQtral, most of the satellite operators who are trying to do the QKD is using simpler one, which is DB QKD. And this, it's actually slightly different. And a lot of people want to somehow integrate it. It's not simple. That's what we are trying to do, right? But for coming back to optical communication, in order to do both, I think basically using optical communication is almost mandatory. Yeah, if you want to do it without radio frequency, I think mostly theoretically not possible. Yeah.
Yeah, and like you guys are building hardware. I mean, Chune, you're launching a satellite next week. What are the technical hurdles that you've run into or challenges that you've seen as far as getting this deployed?
Yeah. Well, multiple challenges. I think just a note to date. I believe only the Chinese has launched successful missions so far. I think 2 key missions and a couple of smaller ones. No one in the world has launched quantum payloads in space and demonstrated long-distance QKD. Well, a couple of experimental ones, but never kind of end-to-end. The challenge is twofold, as I see it. One on the quantum device, and the second challenge is pointing from the satellite to the ground station. So on the quantum device side, we're a little bit more comfortable. We have built 3 quantum devices before that's flown in space. We continue to enhance that device. We've tested and space qualified that in the lab to the 30 dBs of loss from space to ground that we need to undergo. That part, I think we are largely confident. Now, the second portion, which is not our forte or expertise, is the optical terminal and the pointing from spacecraft to ground. That is inherently a huge challenge. The satellite is going at LEO, 7 to 8 kilometers per second. It has to point to a telescope on the ground, which is maybe like 60 centimeter or 80 centimeter, and maintaining that lock. And we are talking about a single photons level. So if the photon doesn't hit the telescope on the ground, it doesn't get registered. So this tremendous, a very, very difficult technical challenge. And this part, hopefully, as the industry progresses, we'll see more capabilities online that we can work together with.
Excellent. Well, just the questions here actually kind of line up nicely with, entangled with the question I was going to ask, which is, would you characterize the development as your hardware is like at the development stage, or is it ready to start generating, like you said, keys as a service, or the security on an optical data relay satellite? So how would you characterize where the technology is today?
So I can go first. As a service provider, well, currently, to be honest, only governments are showing a lot of interest in Japan or Europe or probably in US, including defense. But some of the sectors we hear from like commercial industries such as finance who would like to use this like a QKD in order to protect some of their highly confidential data. So we actually, and those industries like finance and some of the like infrastructure industries in Japan, that's actually interested in utilizing QKD, usually on the ground based, but also utilizing space bit in order to basically have a redundant network. So yes, the technical maturity is one of the biggest topic now. As he mentioned, in order to basically send a single photons, you have to have very precise pointing, and eventually, if you want to use it as a commercial scale, you have to keep sending the photons at very precise angles, and that's a lot of people actually developing a subsystem and the hardware. And well, in several years, I think we will have some more higher data rate application of QKD here.
So a network provider says, hey, I want quantum key distribution tomorrow, or like just immediately. Is there more development required, or is it just a matter of, hey, the time it takes to get a satellite on orbit? Like, how would you guys characterize that?
Yeah, realistically, I think there's still a couple more years to go when before the technology really matures to a service level agreement. So for a network provider that wants kind of a service level capabilities, we'll say that it still takes a couple of years. And there's standards to go, there's certification and so on and so forth. That's probably kind of following the international kind of discussions and standards. But on the government defense side, on the private side, where the customer or the user has internal capabilities on cryptography, on quantum physics, on quantum technologies, they will be able to make that assessment, and they will be able to assess the risk that they want to buy the system. So we think that in the short run, I mean, that's also to the question, in the short run, the main market will come from government defense. They'll assess the systems, and they'll procure hardware, or procure kind of the whole quantum satellites delivered in orbit. And that's the business, is a hardware sale, is a manufacturing kind of provision of the hardware and the software solution. And then, over the midterm, transiting to more commercial QKD service level, where then the network operators can come, they can guarantee to the end customers service level, that you get 99.995% uptime on quantum secure communication. So there's going to be a bit of transition, but we think that obviously the business is here today. There's a lot of interest from especially government defense groups that wants quantum satellites.
All right, I'll just sneak it in right quick. For the audience here, satellite operators that are doing a lot of government business and secure communications, what's your advice to them for adopting quantum? Is any advice?
Well, if you're already doing some of the, national security works, I think lots of, I know like in Europe and US and Japan, and also like, I'm more familiar with some of the incidents in Japan, but even the commercial companies having some cybersecurity issues. So actually interest and also the extra budget for those issues actually, government are trying to invest more in. So I think you can probably include those bit in your proposal. Saying government will show more interest, I think. Yeah.
So, yeah, a quick one. I think my advice for any satellite operators or any players going into the field, don't view the opportunity as a standard business case. You build a business case for 5 or 15 years and you expect an ROI and calculate that. Quantum is not at this stage where you can do that precise forecasting. And if you look at quantum computing companies, there's companies valued at $20 billion on $50 billion of revenues, and there's continuing big investors coming in. So Fidelity International, every week you get news of people investing in technology, and you look at the government, how they're involved, and how they're investing in the quantum tech industry in general. And the first thing is to convince yourself and the management that quantum communication or quantum security is strategic, and then convince yourself there's a real problem in our cryptography or encryption, and that's the starting point. Once you have that ironed out and kind of understood internally, the rest will follow. I mean, there's a lot of people you can talk to enable that business.
Outstanding. All right, well, thank our panelists here, two brilliant individuals. Thank you.
Thank you.
Thank you for the wonderful